Welcome to Ultimate Sleep Doctor. Tonight we turn our gaze upwards. Let's consider the silent dance of our moon, a constant companion in the vast, dark canvas of space. It's a world of ancient craters and hidden shadows, sculpted by eons of celestial influence. The moon, a sentinel of tides and dreams, holds secrets we're only just beginning to understand. Its presence whispers of connection, a reminder that we are part of something infinitely larger than ourselves. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift and find stillness. Let's begin. The early solar system, just a few billion years ago, wasn't the gentle place we see today. It was a chaotic, swirling disk of gas and dust, leftovers from the birth of our sun. This disk, called the protoplanetary disk, was full of tiny particles, grains of rock, ice, and metal, all jostling and bumping into each other. Over immense timescales, these particles began to stick together through electrostatic forces, gradually growing into larger clumps. These clumps formed the building blocks of planets, a process known as accretion. Some of these clumps became protoplanets, embryonic planets still growing, sweeping up more material from the disk. But the story of giant moons doesn't begin with these solitary protoplanets. It begins with a much more dramatic interaction, one involving immense gravitational forces and the delicate dance of tides. The formation of moons, particularly the gigantic ones like Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto, and Saturn's Titan, is primarily linked to a process we call tidal interactions. These interactions didn't occur in a vacuum. They happened within the close proximity of a massive planet and its protoplanetary disk. Initially, a protoplanet, let's call her Proto-Europa, might have formed relatively close to Jupiter. Jupiter, being the most massive planet in our solar system, exerted a huge gravitational pull. This pull wasn't just a gentle tug. It was a powerful force capable of dramatically distorting the shape of anything nearby. As Proto-Europa orbited Jupiter, Jupiter's gravity stretched and squeezed Proto-Europa, much like you might stretch a rubber band. This stretching created bulges on opposite sides of Proto-Europa, generating a tidal force. But here's the crucial part. Jupiter wasn't just pulling on Proto-Europa. Proto-Europa was also pulling on Jupiter. This mutual gravitational interaction was constantly changing the shape of both bodies, generating tidal bulges on both sides. These bulges weren't static. They constantly shifted and moved as Proto-Europa rotated. Now, the energy released during these stretching and squeezing motions wasn't lost. It was converted into heat. This heat was primarily generated within Proto-Europa's interior. The constant flexing and deformation created tremendous friction, like repeatedly bending a metal rod. It gets hot. This internal heating was absolutely vital to the subsequent stages of moon formation. Without this internal heat, the material wouldn't have become fluid enough to be easily processed and incorporated into a larger body. As Proto-Europa continued to orbit and be pulled by Jupiter's gravity, it began to gravitationally sculpt the surrounding protoplanetary disk. Think of it like a sculptor using a chisel to remove material from a block of stone. Proto-Europa, through its tidal interactions, was actively dredging up material from the disk, dust, ice, and small planetesimals, and concentrating it onto its own trailing hemisphere. This trailing hemisphere became a reservoir of material, richer in heavier elements like iron and silicate rock. This process wasn't a single event. It was a prolonged, cyclical one. Jupiter's gravity continuously drew material towards the trailing hemisphere, while the internal heat of Proto-Europa kept this material molten, allowing it to flow and accrete. Over millions and possibly billions of years, this continuous influx of material caused the trailing hemisphere to grow, eventually building up into a substantial mass, the precursor to what we now know as Io, Jupiter's innermost and most volcanically active moon. Simultaneously, this same process was happening, albeit on a smaller scale, with other protoplanets orbiting Jupiter. Ganymede, for example, is believed to have grown through a similar tidal interaction process, though it likely involved interactions with the disk material for a longer duration than Io. The key was the persistent tidal heating and the concentration of material in the trailing hemisphere. Europa, being further from Jupiter, experienced weaker tidal forces, leading to a slower growth rate and a less intensely heated interior. It's important to understand that this tidal accretion mechanism isn't unique to Jupiter's moons. Similar processes are thought to have contributed to the formation of many moons throughout our solar system, particularly around gas giants like Saturn and Uranus. The size and composition of a moon are largely determined by the strength of the tidal forces it experiences and the abundance of material available in its orbital zone. The greater the tidal forces and the more abundant the disk material, the larger the moon tends to grow. Furthermore, the process isn't limited to just the trailing hemisphere. Material could also be drawn in from the leading hemisphere, although this was generally a less efficient process. The leading hemisphere, exposed to Jupiter's gravity and the direct effects of radiation, tended to be depleted of heavier elements. Scientists utilized sophisticated computer simulations and detailed observations of the moon's compositions to refine our understanding of this intricate process. These simulations show just how critical the initial conditions, the orbital distance, the density of the protoplanetary disk, and the angular momentum were to the eventual formation and evolution of these colossal moons. The existence of these giant moons provides a remarkable example of how gravity and tidal forces can sculpt planetary systems. They weren't simply captured objects. They were actively formed through a dynamic interplay between a massive planet and its surrounding environment. The study of giant moons like Jupiter's Galilean moons continues to provide valuable insights into the early stages of planetary system formation and the conditions necessary for the birth of large, complex bodies. It's a story of immense power, slow, sustained change, and the beautiful, complicated dance of gravity. The moon isn't just a silent, dusty sphere hanging in the night sky. Beneath its scarred surface, a surprisingly active history has been unfolding for billions of years. While we often picture the moon as a cold, dead world, evidence has accumulated through careful observation and increasingly sophisticated robotic missions, revealing a complex and dynamic geological past driven by intense volcanic activity. The story of the moon's volcanism begins incredibly early, far before the formation of Earth's oceans, and continues to hold tantalizing clues about the processes that shaped our solar system. Initially, the dominant volcanic style on the moon, what's known as plutonic volcanism, involved the slow, methodical crystallization of magma deep beneath the surface. This wasn't like the explosive eruptions we see on Earth. Instead, molten rock, rich in elements like iron and magnesium, slowly cooled and solidified over vast periods, forming enormous, irregularly shaped bodies of rock called large igneous provinces or lips. These lips, such as the South Pole Wallis Rise and the Naman-Conphilhorn Province, represent some of the largest volcanic events in the solar system's history. They formed over tens of millions of years, creating layered intrusions of rock that can be hundreds of kilometers across. The sheer volume of magma involved is staggering, and the processes that generated it remain a topic of active scientific debate. Some theories suggest that the moon experienced a prolonged period of internal heating, perhaps due to the gradual decay of radioactive elements within its core, while others point to giant impacts as the primary driver of this heat. However, this slow, steady cooling wasn't the whole story. Later in the moon's history, around 3.8 to 3.6 billion years ago, a different kind of volcanism emerged, effusive volcanism. This manifested as the outpouring of lava onto the surface, forming relatively thin, flowing sheets of basaltic rock. The discovery of these flows, primarily through data from the Lunar Prospector and subsequent missions, dramatically shifted our understanding of the Moon's geological evolution. These younger flows, often associated with the formation of lunar maria, the dark, smooth plains that cover a large portion of the Moon's near side, reveal a period of far more vigorous surface activity. The composition of these flows indicates a magma source that was slightly more enriched in aluminum and titanium compared to the plutonic rocks, hinting at a different cooling process and potentially a different source region within the Moon. More recently, within the last few billion years, the Moon has shown evidence of even more recent volcanic activity. The discovery of young volcanic vents and flows on the far side of the Moon, particularly around the Shackleton crater rim, has been one of the most exciting developments in lunar science in recent years. These flows, detected by the Lunar Reconnaissance Orbiter's high-resolution cameras and analyzed through spectral data, suggest that the Moon is still volcanically active, albeit on a much smaller scale than in its early history. The youngest flows are incredibly fresh, indicating they formed within the last 20 to 40 million years. This raises fascinating questions about what's fueling this renewed activity. The source of this contemporary volcanism is believed to be localized reservoirs of heat within the Moon's interior. These reservoirs likely represent pockets of molten rock that are being intermittently mobilized by tidal stresses induced by the Earth's gravity, much like the process that drives volcanic activity on Earth. The Shackleton crater, a massive impact basin, is particularly significant in this regard, creating a highly distorted terrain that exacerbates tidal flexing. This flexing generates heat, and it's hypothesized that this heat is then transferred to the surrounding crust, triggering localized eruptions. The implications of this ongoing volcanism are profound. Firstly, it demonstrates that the Moon isn't a completely inert body. Secondly, and perhaps more importantly, it has significant implications for our understanding of the Moon's interior structure and thermal evolution. The presence of heat sources suggests that the Moon's core remains surprisingly hot, and the distribution of this heat influences the stresses and strains within the crust. Furthermore, the chemical composition of the erupted lavas, particularly the gases trapped within them, provides valuable insights into the Moon's volatile inventory, including water ice, which has been detected in permanently shadowed craters. The discovery of these volatiles is especially exciting because it has potential implications for future lunar exploration and resource utilization. Water ice could be a critical resource for sustaining a lunar base, providing drinking water, oxygen through electrolysis, and propellant for spacecraft. The ongoing volcanism, while currently localized, may be linked to the distribution of this water ice. Looking to the future, scientists are actively monitoring the Moon for signs of more widespread volcanism. Instruments on orbiters and landers are constantly measuring seismic activity, thermal variations, and the composition of the lunar surface. As robotic missions continue to explore the Moon, particularly the permanently shadowed regions of the polar craters, we can expect to uncover even more surprises about this dynamic world. Understanding the Moon's volcanism is not just about understanding the Moon itself. It's about unraveling the complex processes that shape the entire solar system and potentially unlocking resources that could pave the way for humanity's return to the Moon and beyond. The Moon, it turns out, still holds secrets, waiting to be revealed by patient observation and cutting-edge science. The Moon, a serene pearl in the inky blackness of space, is more than just a beautiful sight. Beneath its dusty, cratered surface lies a surprisingly complex system, one that has fascinated scientists for decades. While it doesn't possess a strong, global magnetic field like Earth, the Moon does have a magnetic field, a faint, localized one that plays a crucial role in protecting its surface and influencing its environment. This field isn't a roaring force, but its presence and characteristics deserve our careful attention. The formation of the moon's magnetic field is rooted in its geological history, specifically in the processes that occurred during its early existence. Unlike Earth, which developed a powerful magnetic field through the movement of molten iron within its core, the moon's magnetic field originated from a different mechanism. The moon's core is relatively small and likely composed primarily of silicate minerals, rock-like materials rich in elements like magnesium and iron, but lacking the high concentrations of iron needed for a strong dynamo effect. Instead, the field is believed to have been generated by induced magnetism within the lunar crust. This process relies on the interaction between the moon's crust and the solar wind, a continuous stream of charged particles constantly emitted by the sun. The solar wind isn't just a gentle breeze of particles. It's a turbulent, energetic flow containing ions of hydrogen, helium, oxygen, and heavier elements. When this wind slams into the moon's surface, it interacts with the lunar rocks, particularly those rich in iron and other magnetic minerals. These minerals, acting as tiny magnets themselves, become temporarily magnetized in the direction of the solar wind. This magnetization isn't permanent. It's a dynamic process, constantly being influenced by the ongoing bombardment of the solar wind. The key is that the solar wind doesn't just impact the surface, it also interacts with the underlying crust, creating a patchy, irregular magnetic field. Measuring the strength and extent of this induced magnetic field is a significant challenge. The moon's magnetic field is incredibly weak, estimated to be only about 0.01 to 0.1%, as strong as Earth's magnetic field. Traditional magnetometers, instruments designed to detect magnetic fields, simply don't have the sensitivity to pick up these faint signals across the entire lunar surface. However, scientists have developed sophisticated techniques, primarily using data from lunar orbiters equipped with sensitive instruments like the Gravity Recovery and Interior Laboratory (GRACE) mission, and the Lunar Reconnaissance Orbiter (LRO). GRACE, for instance, detected subtle variations in the moon's gravity, which are closely linked to the distribution of its magnetic field. LRO's magnetometer instrument directly measures the strength and direction of the magnetic field at various locations on the moon. These measurements reveal that the moon's magnetic field is not a uniform blanket, but rather a collection of localized magnetic anomalies. These anomalies are concentrated in certain regions, particularly in the polar areas and in ancient crustal rocks. The nature of these anomalies suggests that the magnetic field is strongest in areas where there is a higher concentration of magnetic minerals, or where the crustal rocks have experienced significant stress and deformation over billions of years. Some of these anomalies are remarkably persistent, suggesting that they represent remnants of the moon's early magnetic activity. The function of this weak magnetic field is surprisingly significant. While it doesn't shield the entire moon from the solar wind, it does provide a degree of protection to the areas where it's strongest. The solar wind interacts with the magnetic field, diverting some of the charged particles away from the surface. This diversion reduces the flux of energetic particles that could otherwise damage the lunar surface, causing weathering and erosion. It's akin to a subtle shield, albeit one that's far less effective than Earth's. Furthermore, the moon's magnetic field plays a critical role in preserving volatile elements, substances like water, ice, and other gases, on the lunar surface. The interaction of the magnetic field with the solar wind helps to trap these volatile elements, preventing them from being easily swept away by the solar wind. Recent discoveries of water ice deposits in permanently shadowed craters at the lunar poles are directly linked to the protective effects of the moon's magnetic field, providing a potential resource for future lunar missions. Scientists believe that the magnetic field actively helps to maintain these cold traps. The distribution of the moon's magnetic field is also linked to lunar tectonics and volcanic activity, although the moon is now geologically inactive. The magnetic anomalies are often found in regions associated with ancient lunar faults and fractures, suggesting that the magnetic field was influenced by the stresses and strains within the lunar crust. Additionally, studies of the lunar magnetic field provide insights into the dynamic processes that shaped the moon's interior in its early history. As the solar wind continues to bombard the moon, the induced magnetic field will continue to fluctuate. However, the long-term stability of the field is uncertain. The gradual depletion of magnetic minerals and the ongoing influence of the solar wind will eventually weaken the field. Nevertheless, understanding the moon's magnetic field remains a vital component of our overall knowledge of the moon's evolution and its interaction with the solar system. It's a testament to the complexity hidden beneath the quiet surface of our lunar neighbor. The moon isn't a perfect sphere, silently reflecting sunlight as we see it from Earth. It's a remarkably complex body, and one of the most fascinating aspects of its nature is a subtle, rhythmic dance, a constant, almost imperceptible wobble called libration. This isn't a violent spinning, but rather a carefully orchestrated tilting of the moon's face, allowing us to see a little bit more than just the near side that we've always known. It's a secret revealed through a delicate shift in perspective, a silent conversation between the moon and our planet. This wobble is primarily caused by two interconnected factors: the moon's elliptical orbit and the inclination of that orbit relative to Earth's equator. You see, the moon doesn't travel in a perfect circle around Earth. Its path is an ellipse. This means its distance from us varies, sometimes closer, sometimes further. As the moon moves closer, the gravitational pull of Earth subtly tugs on it, causing it to stretch slightly along the axis that runs through its center. Simultaneously, the moon is also tilted on its axis by about 5 degrees relative to Earth's orbit, which is itself tilted by roughly 23.5 degrees. This combination creates a complex gravitational interaction, a push and pull that generates the libration. We primarily observe two types of libration. First is libration about the ecliptic. The ecliptic is the plane of Earth's orbit around the sun. Because the moon's orbit is tilted relative to the ecliptic, the moon appears to move slightly north and south of this plane. During a full moon, we see the right side of the moon as viewed from the moon's north pole. However, due to libration, we can actually peek around the back of the moon, seeing the left side, the lunar limb, as viewed from the moon's south pole. This isn't a complete reversal of the entire face, but it's enough to expose approximately 59% of the moon's surface over the course of a lunar month. The second type of libration is longitudinal libration, and this is perhaps even more remarkable. It's a subtle rocking motion that allows us to see a little bit beyond the far side of the moon, beyond what we can observe using traditional telescopes. It's like having a key that unlocks a tiny additional glimpse. Longitudinal libration is predominantly caused by the gravitational influence of the sun. Because the sun's gravity interacts with the moon's orbit, it creates a torque, or a twisting force, that causes the moon to slowly rotate around its axis. This rotation is incredibly slow, taking about 1.66 days to complete a full cycle. Imagine a child spinning a top. The top isn't perfectly stable, it wobbles slightly, and as it wobbles, you can sometimes catch a brief view of the side you couldn't initially see. That's analogous to what's happening with the moon's longitudinal libration. The moon is essentially tipping itself, generating this slow, rocking motion. This particular type of libration allows us to see approximately 8% of the moon's surface, a tiny fraction, but a fraction nonetheless. The data gathered from observing this libration has been invaluable to scientists. By carefully tracking the positions of features on the lunar surface, craters, mountains, and Maria dark, volcanic plains, over many years, astronomers have been able to create a much more detailed and accurate map of the moon than would otherwise be possible. The consistent observations enabled by this wobble have helped to refine our understanding of the moon's shape and its internal structure. Furthermore, understanding libration is crucial for future lunar missions. As spacecraft approach the moon, the ability to accurately predict the moon's apparent position based on this subtle wobble is essential for navigation and for designing landing sites. Without considering libration, landing a spacecraft precisely would be extraordinarily challenging, if not impossible. The patterns of libration aren't uniform. They change over time as the moon's orbit slowly evolves. The angles of libration aren't fixed. They shift subtly over lunar cycles. This dynamic nature of libration requires ongoing monitoring and refinement of our models. Scientists use sophisticated instruments, including laser-ranging reflectors placed on the moon's surface by previous missions, to precisely measure the changes in libration. The study of lunar libration demonstrates that even seemingly simple objects like our moon possess a hidden complexity. It highlights the interconnectedness of gravitational forces and the profound influence of the sun on the moon's behavior. It's a beautiful example of a subtle dance, revealing secrets about the moon's shape, structure, and its relationship with our planet, a silent conversation echoing across the vastness of space. This constant motion, this carefully orchestrated wobble, continues to provide valuable insights, ensuring that our understanding of the moon will continue to evolve. The moon, a silent sentinel circling our planet, has a history far more complex and surprising than most realize. Its surface, a tapestry of craters and ancient plains, tells a story of colossal impacts and gradual, persistent changes. But beneath the visible landscape, a quieter, more insidious process was unfolding for billions of years, the relentless escape of its atmosphere. While the moon doesn't possess a thick, breathable atmosphere like Earth, it did, in the very early stages of its existence, possess a tenuous one, a ghostly echo of the solar nebula from which it formed. This initial atmosphere wasn't rich in the kinds of gases we're familiar with. It was dominated by heavier elements, primarily helium and neon. These gases, far lighter than the materials that constitute the moon's crust and mantle, were carried up from the lunar interior by volcanic activity, creating a delicate, temporary layer. However, this fragile atmosphere wasn't destined to remain. The primary driver of this escape wasn't a sudden cataclysm, but a gradual, unrelenting force: solar wind. The sun, a churning ball of plasma, superheated gas, constantly emits a stream of charged particles, electrons, protons, and ions. This stream, known as the solar wind, carries enormous energy outwards into space. When this wind struck the moon's surface, it didn't just bounce off. Instead, it interacted with the tenuous atmospheric gases, particularly helium and neon. These heavier gases, lacking the mass to withstand the solar wind's outward push, were gradually stripped away, molecule by molecule. The key to understanding this process lies in the concept of momentum transfer. The solar wind particles, moving at incredible speeds, collide with the helium and neon atoms in the lunar atmosphere. These collisions aren't gentle taps, they are forceful exchanges of energy and momentum. The solar wind imparts its motion to the lunar gases, and in doing so, pushes them outwards, away from the moon's surface and into space. It's like trying to stop a rolling ball. The harder you push against it, the faster it accelerates away. Initially, the moon's surface temperature was much higher, due to intense bombardment from space debris and a more active volcanic system. This heat generated a slightly denser atmosphere, and the rate of escape was initially slower. However, as the moon cooled over billions of years, the volcanic activity decreased, and the atmosphere thinned further. Simultaneously, the sun itself evolved. In its early stages, the solar wind was considerably stronger and more energetic than it is today. This higher energy flux accelerated the escape process dramatically. Scientists use sophisticated computer models to simulate this process, incorporating factors such as the sun's evolving output, the moon's surface temperature, and the precise interaction between the solar wind and the lunar atmosphere. These models suggest that the helium and neon weren't simply swept away. They were actively pulled into a stream, a wake, trailing behind the moon as it orbited the sun. This wake, driven by the solar wind, carried these lighter gases away from the moon's vicinity. Measuring the current levels of helium and neon in lunar samples, brought back by the Apollo missions and more recently by robotic landers, provides strong evidence for this ongoing escape. The incredibly low concentrations of these elements, far below what would be expected if the atmosphere had remained intact, demonstrate that this process has been operating continuously for approximately 4.5 billion years. The relative abundance of helium is particularly telling. Helium, with its much lower mass, escapes far more readily than neon, explaining why helium is virtually absent from lunar samples, while neon persists to a slightly greater extent. It's important to note that this escape wasn't a uniform process. The areas of the moon exposed to more direct solar wind exposure, typically the sunlit regions, experienced a greater loss of helium and neon compared to the shadowed, cratered regions. This uneven distribution contributes to the observed variations in elemental abundances across the lunar surface. Furthermore, the escape rate varied over time, coinciding with changes in the sun's activity. Periods of intense solar flares and coronal mass ejections resulted in a temporary increase in atmospheric loss. The implications of this ongoing escape extend beyond simply understanding the moon's past. It offers valuable insights into the evolution of planetary atmospheres throughout the solar system. Many other bodies, including Mars and Mercury, have experienced similar atmospheric losses, and studying these processes helps us understand how planets retain or lose their atmospheres over geological timescales. The moon's story, therefore, isn't just about a single celestial body. It's a microcosm of a fundamental process shaping the habitability of planets across the cosmos. The loss of helium and neon has left its mark on the lunar surface, subtly altering the composition of the regolith, the layer of loose dust and rock covering the moon. While the direct impact of this atmospheric loss on the lunar surface is difficult to quantify precisely, scientists are actively researching its effects, particularly in relation to the stability of lunar soils and their potential for harboring future resources. Understanding this fundamental loss mechanism helps refine our models of the moon's geological evolution and provides a more complete picture of the planet's dynamic history. As the moon continues its endless orbit around Earth, this process of atmospheric escape continues, though at a greatly reduced rate. It's a quiet, invisible process, a testament to the power of the solar wind and a crucial element in explaining the moon's present-day state. It serves as a constant reminder that even the most seemingly solid and enduring objects in space are subject to ongoing change, shaped by forces far grander than ourselves. Ultimately, the story of the moon's atmospheric escape is one of persistence, resilience, and the relentless interaction between celestial bodies and the star that birthed them. It's a chapter in the moon's story that deserves to be understood, not just for its scientific significance, but also for its profound implications regarding the fate of planets throughout the universe. The far side of the moon, often called the dark side, despite being illuminated by the sun like any other portion of our celestial neighbor, holds one of the most enduring and perplexing mysteries in lunar science. For decades, astronomers have observed fleeting, bright spots appearing along the far side's limb, the edge where it meets the blackness of space. These are known as recurring F-limb events, or RFEs, and their precise origins have remained stubbornly elusive, captivating researchers and fueling speculation about unusual geological processes. Initially identified in the late 1960s during the Apollo missions, the first recordings were brief flashes of intense brightness, lasting only a few seconds, and appearing only when the moon was near its zenith, directly overhead. Subsequent observations, made by both ground-based telescopes and spacecraft, have confirmed that these events are consistently recurring, repeating their appearance with remarkable regularity. The The key characteristic of RFEs is their precise timing and location. They almost always emerge from the same region of the far side's limb, typically near the crater Schrödinger, and they follow a predictable cycle. They appear roughly 17 times per year, exhibiting a characteristic footprint of brightness along a narrow arc. This regular recurrence, far more than a random occurrence, strongly suggests a physical process is behind them, something that's happening at a specific location on the moon and repeating with consistent intervals. The initial excitement stemmed from the possibility of discovering entirely new types of lunar geology, potentially even evidence of cryovolcanism, volcanoes that erupt volatiles like water ice or ammonia instead of molten rock. However, the nature of the events remained shrouded in uncertainty. Early hypotheses suggested that the bright spots were caused by reflected sunlight, perhaps intensified by dust particles lofted into the lunar atmosphere. But this didn't fully explain the consistent timing or the specific location. Other ideas included meteoroid impacts, but the brief duration of the events and their regular recurrence made this unlikely. The impact events are typically much longer in duration and have a different spectral signature. The most compelling theory, developed over several years of intensive observation, focuses on the behavior of small amounts of surface material, specifically glassy particles, being ejected into the lunar exosphere. The lunar exosphere is a very thin layer of gas surrounding the moon, composed of atoms and molecules that are constantly being bombarded by the solar wind. These atoms, primarily helium and neon, are very light and easily energized by sunlight. When sunlight strikes these energized atoms, they become excited and then release energy as photons, tiny packets of light. These photons then reflect off the surface, creating the bright flashes that are observed as RFEs. The crucial part of this theory is that these glassy particles, formed during impacts or perhaps from the fracturing of lunar rock by the solar wind, are unusually reflective. They efficiently capture sunlight and re-emit it as bright flashes. Recent observations, particularly using the Lunar Reconnaissance Orbiter's high-resolution cameras, have provided strong evidence supporting this model. Scientists have identified numerous small, glassy particles orbiting the moon, located in the predicted region where RFEs originate. These particles are incredibly fine, ranging in size from microscopic to a few millimeters, and they have a high reflectivity, meaning they bounce a large proportion of the light that hits them. The spacecraft have even been able to track the movement of these particles, confirming that they are precisely the type of material that would efficiently generate the observed RFEs. The discovery of these orbiting particles dramatically shifted the focus of research. Rather than searching for entirely new geological formations, scientists are now investigating the processes that create and maintain these glassy particles. The leading theory suggests that micro-impacts, incredibly small collisions with micrometeorites, are responsible. These impacts don't produce large, easily detectable craters, but they can shatter lunar rocks, creating a spray of glassy material. The solar wind then sweeps this material into the exosphere, where it remains for a relatively short period before being further energized and eventually lost to space. It's important to note that the RFEs are not constant, bright beacons. They are fleeting events, lasting only seconds, and their intensity can vary. This variability is linked to the amount of sunlight hitting the orbiting particles and the level of solar wind activity. When the sun is directly overhead, the particles are bathed in intense sunlight, generating brighter flashes. Conversely, during periods of low solar wind activity, the flashes are weaker. Furthermore, the lifetime of the orbiting particles is also affected by solar wind conditions. Stronger solar winds can strip the particles away from the moon. Despite considerable research, many questions about RFEs remain unanswered. The exact mechanisms responsible for creating the initial glassy particles is still debated, and the long-term stability of the orbiting material, how long it persists in the exosphere, is also unclear. There is ongoing investigation into whether any of these orbiting particles are being influenced by the Moon's magnetic field, a field considerably weaker than Earth's, and whether there might be a connection between the RFEs and the subtle changes in the lunar exosphere. The study of RFEs continues to be a dynamic field of lunar science, driven by the tantalizing possibility that these fleeting events could provide unprecedented insights into the composition, dynamics, and evolution of our nearest celestial neighbor. It's a testament to the power of persistent observation and the ingenuity of scientists seeking to unravel the secrets hidden on the far side of the Moon. The continuing investigation of these mysterious flashes remains one of the most exciting areas of lunar research today. The Moon, a silent sentinel in our night sky, isn't a smooth, featureless sphere. Looking closely at images returned by lunar orbiters, you'll notice vast, dark plains, incredibly smooth and flat, covering nearly 15% of its surface. These are what we call lunar mare, Latin for seas, a name given by early astronomers because they resembled the dark oceans on Earth. But these aren't actually water. They're solidified basalt, a dark, fine-grained volcanic rock formed by ancient eruptions that flooded these low-lying regions. The largest of these basins, like Mare Tranquillitatis, Sea of Tranquility, and Mare Imbrium, Sea of Rains, are immense, some stretching over 300 kilometers across. Their formation isn't a slow process of gradual accumulation. Instead, they represent the remnants of colossal impacts, scars etched into the Moon's surface by events of extraordinary power. The dominant theory explaining the existence of the Mare basins, and indeed much of the Moon's heavily cratered surface, is the giant impact theory. It's a story of a dramatic collision billions of years ago, a collision so energetic it fundamentally reshaped the early solar system. Initially, the theory proposed a single, catastrophic event. A Mars-sized object, often dubbed Theia, slammed into the proto-Earth. This impact didn't just fling a huge chunk of Earth into orbit, forming the Moon. It also vaporized a significant portion of both bodies. The debris from this collision, molten rock, dust, and shattered fragments, coalesced under the influence of gravity, gradually forming the Moon. However, the initial model faced significant challenges. The energy required to completely obliterate a Mars-sized object and still leave the Moon relatively intact was simply too high. Furthermore, the theory struggled to explain the precise distribution of the Mare basins. Why were they concentrated in specific regions, and why were they so large? It wasn't until advancements in computer modeling and analysis of lunar samples that the theory began to gain more compelling support. The key development came with the recognition that the impact wasn't a single event, but rather a series of collisions, perhaps triggered by the gravitational influence of Jupiter and Saturn. These giant planets had immense gravitational pull, stirring up the early solar system and sending objects, including Theia, on trajectories that eventually led to collisions with Earth. Later impacts, smaller than the initial one, continued to flood the low-lying areas, creating the vast, dark Mare basins we observe today. Evidence supporting the giant impact theory is multifaceted. Firstly, the isotopic composition of lunar rocks, specifically the ratio of oxygen isotopes, strongly suggests a significant contribution from a separate material body, likely Theia, that wasn't originally part of Earth. The isotopic signatures are markedly different from those found in Earth's crust, indicating an external source. Secondly, the distribution of Mare basins aligns remarkably well with simulations of giant impacts. Computer models, incorporating factors like gravitational interactions, impact angles, and material properties, consistently produce impact basins mirroring those observed on the Moon. These simulations allow scientists to tweak the parameters, the size of Theia, its velocity, the angle of impact, and see how these changes affect the resulting crater distribution. The closer the model's output matches the real-world data, the stronger the support for the theory. While initial models produced excessive cratering, refinements based on factors like the moon's rotational speed and the presence of a tenuous early atmosphere allowed for a more plausible scenario. There are still debates and uncertainties within the giant impact theory. The precise size and composition of Theia remains somewhat unclear, although recent research suggests it may have been slightly smaller than previously thought. Furthermore, the nature of the early lunar atmosphere, if it existed at all, and its role in shaping the mare basins is still being investigated. Some researchers propose that volcanic activity, fueled by heat from the impact, played a more significant role in filling the basins than initially assumed. Another ongoing area of research focuses on the possibility of multiple impact events, rather than a single, dominant collision. The presence of some mare basins that seem unusually large or irregularly shaped suggests the possibility of secondary impacts, triggered by the initial event and subsequent gravitational disturbances. Analyzing the ages of the mare basalts, dating the timing of the volcanic eruptions, is crucial for refining our understanding of the timing and sequence of these events. Despite these uncertainties, the giant impact theory remains the most compelling and widely accepted explanation for the origin of the moon and the formation of its distinctive mare basins. It's a testament to the dramatic and violent processes that shaped our solar system in its infancy. The dark plains of the moon, these vast, ancient seas of basalt, are not just geological features. They are physical witnesses to one of the most cataclysmic events in the history of our planet, a story etched in stone and forever reflected in the silent, watchful gaze of the moon. The moon isn't a perfectly still companion in the night sky. It's been spinning, slowly and steadily, for billions of years, but the rate at which it spins hasn't always been the same. The story of the moon's rotation is deeply intertwined with its journey around the Earth, a complex dance of gravitational forces and energy transfer that has shaped both celestial bodies in profound ways. Initially, the moon likely rotated much faster than it does today, perhaps with a day, the time it takes for one full rotation, lasting only a few hours. This rapid spin is believed to have been influenced by a surprisingly violent early history. The early moon, shortly after its formation, was bombarded by countless asteroids and comets. These impacts weren't gentle nudges. They were immense collisions carrying tremendous kinetic energy. Some scientists believe that these impacts imparted a significant amount of angular momentum to the moon, essentially winding up its rotation like a spinning top. The problem is that energy couldn't simply disappear. The laws of physics dictate that angular momentum, the measure of an object's rotational motion, must be conserved. When the moon received this extra spin, some of that energy had to go somewhere. And where did it go? It transferred to the Earth. This transfer wasn't a sudden, dramatic event, but rather a gradual, ongoing process. The moon's faster rotation slowed down slightly, and simultaneously, the Earth began to rotate a little faster. It's a reciprocal exchange, a constant borrowing and lending of energy. The exact mechanisms of this energy transfer are still being investigated, but scientists believe tidal forces played a crucial role. The tides, the rise and fall of ocean water, aren't just caused by the moon's gravity, they're also a conduit for energy transfer. As the moon's gravity pulls on the Earth, it creates bulges of water on both the side of Earth facing the moon and the side opposite it. These bulges move with the moon as it orbits. The water, being fluid, doesn't simply move in line with the moon's orbit. It's constantly being pulled back and forth by the gravitational forces. This constant back and forth motion, coupled with the friction generated by the movement of water against the seabed, effectively converts some of the moon's rotational energy into heat, which then dissipates into space. Over billions of years, this continuous exchange has dramatically altered the moon's rotation. Calculations based on lunar samples and observations suggest that the moon's rotation period has slowed down by approximately 50 to 60% since its formation. This means that the moon's day was once considerably shorter than it is now, perhaps just 14 to 18 hours. The Earth's rotation also changed, although the effect on Earth's rotation is less pronounced because Earth is much larger and more massive than the moon. The slowing process wasn't uniform. There were periods of acceleration and deceleration. There's evidence suggesting that around 3.8 billion years ago, the moon's rotation actually sped up slightly. This acceleration is linked to the formation of the Imbrium Basin, one of the largest impact craters on the moon. The immense energy released during this colossal impact likely caused a sudden redistribution of momentum within the moon's interior, momentarily increasing its rotational speed. Following this acceleration, the moon resumed its gradual slowing trend. Furthermore, the moon isn't perfectly spherical, it's slightly elongated. The far side of the moon, the one we never see from Earth, is noticeably bulgier than the near side. This asymmetry in shape has a significant impact on its rotation. The bulges on the far side experience a greater gravitational pull from the Earth, which creates a torque, a twisting force, that further contributes to the slowing of the moon's rotation. Think of it like a figure skater pulling in their arms. The movement of mass creates a rotational effect. Scientists use sophisticated models, incorporating data from lunar seismometers, ranging observations, and detailed computer simulations, to reconstruct this complex history. These models allow them to refine their understanding of the energy transfer mechanisms and to predict how the moon's rotation will continue to evolve in the future. While the slowing process is currently very slow, only a few milliseconds per century, it's a testament to the ongoing interplay between the Earth and its lunar companion. The moon's slowing rotation isn't just a fascinating scientific puzzle. It also has profound implications for understanding the early history of our solar system. By studying the moon's rotation, scientists can gain valuable insights into the processes that shaped the Earth and other planets during their formation. It's a story of energy, momentum, and the enduring dance between two celestial bodies, a story that continues to unfold with each passing orbit. And as we continue to explore the moon, we will undoubtedly uncover more secrets about this remarkable and ancient world. The moon's surface isn't a smooth, blank canvas. It's a wildly textured landscape, a record of billions of years of collisions and volcanic activity. Understanding this surface requires us to delve into the processes that created its most prominent features: craters, maria, and highlands. These aren't just random bumps and plains. They represent vastly different ways the moon was built and reshaped over eons. Let's begin with craters. They are perhaps the most recognizable feature of the lunar surface, and they tell a very direct story of bombardment. For a long time, scientists believed the moon was largely undisturbed, a silent sentinel. However, observations of numerous impact craters, ranging in size from tiny, bowl-shaped depressions to enormous basins hundreds of kilometers across, quickly revealed a shocking truth. The moon was relentlessly hit by asteroids and comets. These objects, flung out from the early solar system, were on a collision course with the young, fragile moon. The size of a crater depends primarily on the size and velocity of the impacting object, as well as the composition of the lunar surface at the point of impact. Smaller objects, often just a few meters across, create simple, bowl-shaped depressions. Larger impacts, however, trigger a far more dramatic sequence of events. When a substantial asteroid or comet strikes the moon, the intense heat generated by the collision doesn't just vaporize the object itself. Instead, it vaporizes a significant portion of the lunar rock beneath the impact site, creating a shockwave that propagates outwards. This shockwave fractures and shatters the surrounding crust, generating a temporary melt pool. The resulting crater is often complex, with a central peak, formed by the rebound of the crust after the initial shock and terraced walls. The size of the central peak is directly related to the energy of the impact. The larger the impact, the higher the central peak. Furthermore, the force of the impact excavates a large chunk of material, throwing it outwards as ejecta, fragments of rock and dust, propelled high into the atmosphere. This ejecta blankets the surrounding area, forming a ring of debris around the crater. Scientists study the composition of this ejecta to learn more about the moon's internal structure and the materials that make up its crust. Now, let's move on to the vast, dark plains we call Maria, which translates to seas in Latin. Despite their name, they are not actually composed of water. Instead, the Maria are enormous, relatively smooth plains formed by ancient volcanic eruptions. Unlike the heavily cratered highlands, the Maria are remarkably young, dating back to the period from about 3.8 to 1.2 billion years ago. These eruptions weren't like volcanic eruptions on Earth. They were incredibly powerful, releasing huge volumes of molten rock, basalt, from the moon's interior. This molten rock flowed across the surface, filling in pre-existing impact basins and creating the expansive plains we see today. The lava was unusually fluid due to the lack of atmospheric pressure to cool it quickly, allowing it to spread across vast distances. The dark color of the Maria is due to their composition. They're rich in iron and magnesium, which absorb more sunlight than the lighter-colored highlands. The highlands, in stark contrast to the Maria, are the oldest and most heavily cratered regions of the moon. They cover roughly 2/3 of the lunar surface and represent the remnants of the moon's early formation. They are characterized by their rugged, mountainous terrain and are littered with countless impact craters, the scars of billions of years of bombardment. The highlands are composed of an igneous rock called anorthite, which is rich in calcium and aluminum. This material formed the crust of the early moon and was largely untouched by the intense volcanic activity that created the Maria. The craters in the highlands are incredibly old, providing a detailed record of the early solar system's bombardment period. Scientists can even study the layering within these craters to understand the evolution of the lunar crust over time. The distribution of these features isn't random. The Maria are clustered along the lunar equator, largely because this is where the moon's rotational axis was tipped during its formation. This tilt explains why the volcanic activity was concentrated in this area, as it created a stronger gravitational pull towards the equator, driving the movement of magma. The highlands, being furthest from the equator, experienced less gravitational influence and consequently, less volcanic activity. Ultimately, the lunar surface is a stunning testament to the dynamic history of our solar system. The craters, Maria, and highlands aren't just geological features. They're a visual diary of collisions, volcanic flows, and the slow, relentless processes that have shaped the moon into the celestial body we observe today. Studying these features allows us to piece together a story of the early solar system, a story written in rock and dust, a story that continues to unfold as we learn more about our nearest neighbor in space. The moon's gentle glow, a constant companion to our night, isn't just a beautiful sight. It's intimately connected to one of the most dramatic and persistent displays of natural power on Earth, the tides. The relationship between the moon and our oceans isn't a static thing. It's a constantly shifting dance dictated by the moon's gravity and Earth's rotation. Understanding this interaction reveals a surprisingly complex and vital system that governs a significant portion of our planet's surface. The key to understanding this connection lies in the concept of gravity. Gravity is a fundamental force of attraction between any two objects with mass. The more massive an object is, the stronger its gravitational pull. The moon, despite being considerably smaller than Earth, possesses a substantial mass, and this mass exerts a gravitational force upon Earth. This force isn't uniform across the planet. It's strongest nearest the moon and weakens as you move further away. Now let's consider the ocean. Water, like all matter, is also subject to gravitational forces. The moon's gravity pulls the water on the side of Earth facing the moon towards it. This creates a bulge of water, a high tide. However, it's not just the side facing the moon that experiences a high tide. This is where the Earth's rotation comes into play. As the Earth spins on its axis, a location on Earth is constantly moving away from the moon. Simultaneously, the moon's gravity continues to pull on that location. This creates a second bulge of water on the opposite side of the Earth. Think of it like this. The moon is pulling the Earth and the water around it, and because the Earth is also moving, the water gets stretched along with it, creating a second bulge. These two bulges, one on the side of Earth facing the moon and another on the opposite side, represent the high tides. As Earth rotates, different locations pass through these bulges, experiencing a high tide, while the areas between the bulges experience low tide. This cycle repeats approximately every 12 hours and 25 minutes. This slight variation in the period, 25 minutes, is due to the moon's elliptical orbit. It's not a perfect circle, but an egg shape. The tides aren't solely caused by the moon, though. The sun also plays a significant, albeit smaller, role. The sun's gravity also pulls on the Earth and the oceans. When the sun, Earth, and moon are aligned during new and full moons, their gravitational forces combine, creating particularly strong tides known as spring tides. These spring tides are characterized by higher than usual high tides and lower than usual low tides. Conversely, when the sun and moon are at right angles to each other relative to Earth, during the first and third quarter moons, their gravitational forces partially cancel each other out. This results in weaker tides called neap tides, with less pronounced differences between high and low tide. It's important to recognize that the shape of coastlines and ocean basins dramatically influences tidal patterns. Narrow bays, estuaries, and shallow waters can amplify tidal ranges, meaning the difference between high and low tide is greater. Conversely, deep, open oceans generally experience smaller tidal fluctuations. The complex interplay of these geographical factors creates incredibly diverse tidal patterns around the globe. Furthermore, the tides aren't just about water rising and falling. The movement of water creates powerful currents that influence marine life, transport sediment, and shape coastal environments. These tidal currents can be incredibly strong, capable of eroding coastlines and transporting vast quantities of water. Scientists use sophisticated models and measurements to study tidal patterns. These models take into account the positions of the sun and moon, the shape of coastlines, and other factors to predict tidal movements with increasing accuracy. These predictions are crucial for navigation, coastal management, and understanding the delicate balance of marine ecosystems. The gravitational dance between the moon and Earth is far more than just a visual spectacle. It's a fundamental driver of processes shaping our planet. It's a constant reminder of the interconnectedness of celestial bodies and the powerful forces that govern our world, influencing everything from the rhythm of the oceans to the shape of our coastlines. The moon's pull continues, a silent, steady influence on the tides, a timeless story etched in the rise and fall of the waves. The moon, a seemingly silent sentinel in our night sky, holds secrets within its very surface, secrets wrapped up in a remarkable and surprisingly complex material: lunar dust. This isn't just any dirt. It's a finely ground, abrasive substance unlike anything found on Earth. It's formed over billions of years through a constant process of micrometeorite bombardment and the mechanical weathering of the lunar rock. The initial formation of this dust is a story etched in the moon's history, a testament to the ceaseless impacts that have shaped its appearance. These impacts, though less dramatic than the large craters we see, consistently erode and grind down the surface, releasing tiny, glassy particles, the beginnings of what we now recognize as lunar regolith. This regolith, as scientists call it, isn't just a collection of small rocks. It's a surprisingly heterogeneous mixture, containing everything from glassy spherules, almost like tiny solidified raindrops of molten rock, to sharp, angular fragments of rock and metal. The size distribution is incredibly fine, with a significant portion of the dust measuring less than a micrometer in diameter. This fine grain size is crucial to understanding its unique properties. It's remarkably lightweight, about a sixth of the density of soil on Earth. This low density is a direct consequence of the immense vacuum of space, where the dust is not held together by gravity as strongly as it would be on our planet. The particles are essentially floating in a sea of emptiness, contributing to their slipperiness. One of the most concerning aspects of lunar dust is its abrasiveness. It's shockingly sharp and capable of causing significant damage to equipment and, worryingly, potentially to human health. This isn't due to any inherent nastiness in the dust itself, but rather its unique physical characteristics. The tiny, sharp particles act like microscopic sandpaper, rapidly eroding surfaces. Even seemingly durable materials like Teflon, commonly used for seals and bearings, can be severely worn down by prolonged exposure. This has been repeatedly demonstrated during lunar missions, most notably during the Apollo program, where dust infiltrated suits, clogged machinery, and damaged cameras. The dust's ability to stick to surfaces, even in a vacuum, further exacerbates the problem, creating a tenacious coating that's incredibly difficult to remove. The electrostatic charging of lunar dust plays a significant role in its behavior and hazards. In the vacuum of space, dust particles readily acquire an electrical charge, typically through triboelectric charging, a process that happens when different materials rub against each other. This charging is intensified by the dust's low conductivity and its ability to trap static electricity. Once charged, the dust becomes incredibly mobile, readily sticking to surfaces and even levitating in the air. This electrostatic attraction is a primary reason why dust has been observed drifting across the lunar surface, creating miniature dust devils. The increased mobility of charged dust also dramatically increases its abrasiveness. A charged particle is much more likely to stick to and grind against a surface than an uncharged one. Looking ahead, the challenges posed by lunar dust are central to the planning of future lunar exploration missions, particularly those involving long-duration stays on the Moon. NASA's Artemis program, aiming to establish a sustainable human presence on the Moon, is investing heavily in technologies designed to mitigate the dust's impact. Current research focuses on developing specialized suits and equipment with electrostatic shielding, dust-repellent coatings, and effective cleaning systems. These systems often employ brushes, vacuums, and electrostatic dust removal techniques. Furthermore, innovative designs for habitats and rovers are incorporating features that minimize dust accumulation and facilitate its removal. Beyond simply protecting equipment, scientists are investigating the potential uses of lunar dust. Surprisingly, it's a valuable resource that could be utilized for various purposes. The regolith contains elements like oxygen, aluminum, and titanium, which could be extracted and used to create propellant, construction materials, and even radiation shielding. Techniques are being developed to process the regolith into a lunar concrete, a durable material that could be used to build habitats and infrastructure on the Moon. The extraction of oxygen is particularly exciting, as it could provide a readily available source of propellant for return journeys to Earth or for further exploration of the solar system. The study of lunar dust is also providing valuable insights into the early history of the solar system. By analyzing the composition and structure of the regolith, scientists can learn about the processes that shaped the Moon and the conditions that existed during its formation. The dust acts as a time capsule, preserving remnants of ancient impacts and volcanic activity. Furthermore, the dust's unique properties offer a valuable testing ground for materials science and engineering, pushing the boundaries of what's possible in extreme environments. As we venture further into the cosmos, understanding and managing lunar dust will undoubtedly remain a critical factor in our success. The Moon's dust, a seemingly simple material, is therefore a surprisingly complex and vital piece in the puzzle of humanity's exploration of space. The moon's surface, so familiar from countless photographs, isn't a static, unchanging landscape. It's a remarkably sensitive thermometer, constantly reacting to the sun's presence and absence. The temperature of the lunar environment fluctuates dramatically, far more than most people realize. This isn't due to a gradual warming or cooling. It's a series of incredibly sharp shifts, driven by the most basic of principles, radiation from our nearest star. The primary driver of this temperature dance is solar radiation. When the sun is directly overhead, shining its brightest, the lunar surface absorbs this energy, heating up rapidly. The dark basaltic rock that makes up much of the lunar maria, or seas, is particularly efficient at absorbing sunlight, making these areas significantly warmer than the surrounding highlands. These maria, formed by ancient volcanic flows, possess a high solar absorptivity, meaning they readily soak up the sun's energy. However, this intense heat is fleeting. As the moon rotates on its axis, a lunar day, the period of time when the sun illuminates a particular region, progresses. The absorption of solar energy continues until the surface temperature reaches a maximum, typically around 127 degrees Celsius, 260 degrees Fahrenheit, during the peak of a lunar day. This isn't a comfortable temperature, of course, and it's a reminder of the intense energy the moon receives. The lack of an atmosphere, unlike Earth's, plays a crucial role in this rapid heating and cooling. Without an atmosphere to trap and redistribute heat, the energy remains concentrated on the surface. As the sun begins to set, the angle of incidence changes. Sunlight strikes the surface at a shallower angle, and a much larger area is exposed to the direct rays. The heat absorbed is less concentrated, and the rate of heating decreases. This transition marks the beginning of a lunar night, which is, astonishingly, just as long as a lunar day, approximately 14 Earth days. During this period, the surface temperature plunges dramatically. The basaltic rock, now unexposed to direct sunlight, radiates its stored heat back into space. This radiative cooling is a fundamental process. Any object that has absorbed energy will eventually release that energy as heat. The temperature drop during a lunar night is even more extreme. Without an atmosphere to buffer the heat loss, the surface can cool to as low as minus 173 degrees Celsius, minus 280 degrees Fahrenheit. This astonishingly cold temperature isn't uniform across the moon's surface. The highlands, composed of lighter, more porous rock, have a lower solar absorptivity than the maria. Consequently, they heat up more slowly and cool down more slowly, resulting in a smaller temperature variation. The rugged, mountainous terrain of the highlands, marked by numerous craters and ancient volcanic features, amplifies this effect. These areas retain heat for a longer duration, moderating the extreme temperature swings. The lunar regolith, the loose, powdery layer covering the surface, also plays a significant role in modulating temperatures. This layer, created by billions of years of micrometeorite impacts and solar wind bombardment, acts as an insulator. It's not a perfect insulator, but it does reduce the rate at which the underlying rock loses heat during the night and absorbs heat during the day. The texture and composition of the regolith vary across the moon, leading to further localized temperature differences. Some areas are covered in fine, dust-like particles, while others have larger rocks and pebbles. These variations influence the thermal conductivity of the surface. Furthermore, the moon's rotation isn't perfectly stable. It's gradually slowing down, a process known as tidal deceleration. This slight change in rotation affects the duration of the lunar day and night, and therefore, the extreme temperature variations. As the moon's rotation slows, the length of each day and night will continue to increase, impacting the magnitude of the temperature fluctuations. Scientists precisely measure these changes, providing valuable insights into the moon's internal dynamics. The absence of an atmosphere also means that there is no wind to distribute heat across the surface. Any temperature differences are isolated. This lack of atmospheric circulation creates a stark and surprisingly distinct thermal landscape. The lunar surface presents a truly remarkable contrast, highlighting the powerful influence of solar radiation and the fundamental laws of thermodynamics. It's a constant reminder of the stark differences between our world, warmed by our atmosphere, and this silent, cold neighbor in space. The study of these temperature variations isn't just an academic exercise. Understanding the lunar thermal environment is crucial for planning future human missions. Knowing how the surface temperature changes will dictate the materials needed for habitats, the types of equipment required, and the strategies for protecting astronauts from extreme heat and cold. The moon's thermal behavior is a delicate balancing act, a fascinating demonstration of physics playing out on a grand scale. Ultimately, the moon's temperature story is a story of extremes, a testament to the power of the sun and the moon's isolation. It's a landscape sculpted by heat and cold, a silent record of solar cycles, and a powerful example of how our celestial neighbors are inextricably linked to us, even from the vast emptiness of space. The moon, a silent sentinel in our night sky, holds secrets within its shadowed craters and ancient plains. For decades, scientists have suspected the presence of water ice, a possibility that has steadily grown into a compelling and increasingly detailed reality. The evidence isn't just a fleeting hypothesis, it's building a picture of the moon's past and potentially its future. Initially, the search for water ice was driven by the desire to understand the moon's geological history, how it formed, how it has changed over billions of years, and whether it might have ever harbored conditions suitable for life. Now, the focus is shifting towards utilizing this resource to support human exploration and establish a permanent presence. The most compelling evidence for water ice comes from radar observations. Specialized radar instruments, like those aboard the Lunar Reconnaissance Orbiter, LRO, can penetrate the lunar surface. These instruments send out radio waves and analyze the reflections. What they've found is astonishing. Large, bright radar reflections concentrated in permanently shadowed craters near the moon's poles. These craters, especially those within the Shackleton crater, a vast depression at the South Pole, measuring roughly 27 miles across, consistently exhibit these strong signals. The reflectivity is remarkably high, indicating a significant concentration of material, and the radar data strongly suggests that material is water ice. The key to understanding this discovery lies in the concept of cold traps. These permanently shadowed regions never receive direct sunlight. Consequently, the temperature within these craters can plummet to incredibly low levels, far colder than anywhere else on the moon. This extreme cold is absolutely crucial because it allows water molecules to exist in a solid, frozen state for extended periods, shielded from the intense solar radiation and the volatile effects of space. Scientists estimate the temperature at the bottom of Shackleton crater can be as low as -240 degrees Celsius, -392 degrees Fahrenheit. The abundance of ice isn't uniform across these permanently shadowed areas. Initial estimates, based on radar data and preliminary surface analysis, suggest that there could be anywhere from a few kilograms to potentially hundreds of kilograms of water ice per square meter in the deepest parts of these craters. However, the exact quantity remains uncertain, and ongoing research is attempting to refine these estimates. It's important to note that the ice isn't simply sitting on the surface. It's believed to be mixed with lunar regolith, the loose, rocky soil covering the moon's surface. This mixture creates a complex environment, and understanding its composition is a major challenge for researchers. Beyond the South Polar region, evidence for water ice is also emerging in other permanently shadowed areas across the lunar surface. Smaller, less concentrated deposits have been detected using radar, primarily in craters at higher latitudes. These findings suggest that the distribution of water ice on the moon might be more extensive than initially thought, potentially spanning across a significant portion of the polar regions. Recent data from the Chandrayaan-2 orbiter, India's lunar mission, has confirmed the presence of water molecules detected by the orbiter's instruments, adding further weight to the evidence. Scientists are exploring various methods to accurately determine the total amount of water ice present on the Moon. One approach involves analyzing the composition of the lunar regolith within these permanently shadowed regions. Robotic missions, such as NASA's Viper, Volatile's Investigating Polar Exploration rover, are specifically designed to land in these areas and directly sample the soil. Viper's primary goal is to determine the concentration of water ice and other volatile compounds, providing invaluable data for future resource utilization. The rover will analyze the soil composition and, crucially, attempt to extract and analyze water samples. The potential uses of lunar water ice are vast. Primarily, it can be used to produce rocket propellant, liquid hydrogen, and liquid oxygen, a critical resource for fueling spacecraft during journeys to Mars and beyond. Transporting propellant from Earth is incredibly expensive. Utilizing locally sourced water ice would dramatically reduce the cost and complexity of deep space exploration. Furthermore, water ice can be electrolyzed, broken down using electricity, to produce breathable oxygen for astronauts and hydrogen, which can be used as a fuel or for other applications. Beyond propellant production, water ice could also be used to create drinking water, generate electricity through thermoelectric devices, and even construct building materials for lunar habitats. The ability to create a sustainable resource base on the Moon would be transformative, enabling long-term human settlements and serving as a stepping stone for further exploration of our solar system. The current estimates, while still subject to refinement, paint a picture of the Moon as potentially holding a valuable, strategically important resource, a testament to the Moon's enduring secrets and a beacon of opportunity for future generations. Analyzing the ice's purity and managing its extraction will be paramount, but the very fact that it's there provides an unprecedented advantage in our ambitions to reach for the stars. The Moon isn't a silent, lifeless rock. Beneath its dusty surface and familiar craters, there's a surprisingly active geology, driven by forces remarkably similar to those that shape our own planet, Earth. While we often think of earthquakes as being solely linked to plate tectonics, the grinding and shifting of massive sections of Earth's crust, the Moon experiences a different kind of seismic activity, one driven by a vastly different set of processes. These aren't the dramatic, continent-spanning earthquakes we experience on Earth. Instead, they're typically smaller, more localized events, often referred to as lunar quakes or moonquakes. The initial detection of lunar seismic activity came in 1966 during the Apollo 12 mission. Scientists operating seismometers, instruments that detect and measure ground vibrations, placed on the Moon's surface recorded distinct vibrations. These weren't random noise. They followed patterns, indicating a genuine source of energy within the Moon. The Apollo missions deployed a network of these instruments, allowing scientists to build a much more detailed picture of the Moon's internal structure and the nature of these tremors. The recordings revealed three main types of lunar quakes: tremors, pulsations, and impacts. Tremors are the most common type of lunar quake. They're characterized by a slow, sustained vibration, lasting anywhere from a few minutes to several hours. These tremors are believed to be primarily caused by the relaxation of stresses within the lunar crust. Just like a tightly stretched rubber band will eventually snap back into shape, the Moon's crust isn't perfectly rigid. Over billions of years, the constant bombardment from meteoroids and the gravitational pull of Earth and the Sun create internal stresses. These stresses gradually release, causing slow, rhythmic vibrations. The amplitude or strength of these tremors varies, with some lasting for extended periods and emitting powerful vibrations, while others are brief and weaker. Researchers analyze the frequency and duration of these tremors to understand the composition and layering of the lunar crust. Pulsations, on the other hand, are distinct from tremors. They're characterized by a sudden, sharp increase in ground motion, followed by a rapid decline. These events typically last for a few seconds to a minute and are thought to be associated with the fracturing of the lunar crust. Imagine a delicate shell cracking under pressure. That's a simplified way to think about what's happening during a pulsation. Scientists believe these pulses are triggered by the unloading of stress when the moon's interior cools slightly, causing the crust to contract and fracture. The precise mechanisms triggering these events are still being investigated, but they offer crucial data about the moon's mechanical properties. Furthermore, the relationship between pulsations and the moon's thermal environment is an area of ongoing research. As the moon experiences cycles of heating and cooling, due to its rotation and its orbit around Earth, the stresses within the crust shift, leading to these sudden bursts of seismic activity. The timing of pulsations often correlates with changes in surface temperature, offering a valuable link between the moon's thermal behavior and its internal dynamics. Then there are the impacts, and these are truly remarkable. Unlike Earth, where most impacts are relatively small and quickly dissipate, the moon's lack of atmosphere and water significantly amplifies the effects of impact events. When a meteoroid strikes the moon's surface, the energy is not absorbed and dispersed as it would be on Earth. Instead, it's transmitted through the entire lunar crust, creating a powerful, short-lived seismic event. These impact quakes can be far more intense than typical tremors or pulsations, lasting from seconds to even several minutes. The Apollo missions recorded some of the largest lunar quakes ever detected, all triggered by meteoroid impacts. These events provide invaluable information about the size and frequency of meteoroid bombardment throughout the moon's history. Studying the seismic signatures of these impacts helps scientists reconstruct the history of the solar system and understand how the moon has been shaped by countless collisions. The Apollo 15 mission recorded the largest recorded lunar quake, measuring 4.7 on the Richter scale, caused by a meteoroid impact. The distribution of these seismic events isn't uniform across the moon's surface. Certain regions, particularly those with more complex geological features and variations in crustal thickness, experience more frequent and intense quakes. For example, the Marius Hills region is known for its high seismic activity, while the Serenitatis Basin, a large impact crater, exhibits frequent tremors. This spatial variation provides clues about the underlying geological structures and the distribution of stress within the lunar crust. Scientists utilize sophisticated computer models to simulate the moon's internal structure and test different scenarios to explain the observed seismic activity. These models incorporate data from seismological observations, along with information about the moon's age, density, and composition. By comparing the predictions of these models with the actual seismic data, researchers can refine their understanding of the moon's interior and develop more accurate models. Interestingly, the seismic activity on the moon is generally weaker than that found on Earth. This is primarily because the moon has a much smaller mass and a significantly different internal structure. Furthermore, the lack of plate tectonics, the process that shapes Earth's continents, means there's no mechanism for releasing accumulated stress in the same way. However, the study of lunar quakes continues to be a vital component of our understanding of the moon, providing key insights into its formation, evolution, and potential resources. As future missions return to the moon, including those planned for the Artemis program, the collection of more seismic data will undoubtedly lead to even greater discoveries about this fascinating and dynamic celestial neighbor. Our story about the moon has taken us on a fascinating journey, revealing its unique characteristics and the secrets hidden within its rocky surface. We've explored the way its temperature fluctuates, the evidence suggesting ancient water ice, and even the surprising tremors that occasionally ripple through its crust. But the moon isn't an isolated wonder. Its story isn't the only one unfolding in our vast solar system or beyond. Astronomers are increasingly focused on understanding the moons orbiting other planets, a field known as exomoon research. These moons, existing around stars other than our Sun, present a tremendously exciting and challenging area of study, offering the potential to revolutionize our understanding of planetary formation and the prevalence of life-supporting environments. Initially, the search for exomoons was largely theoretical. Detecting them directly is extraordinarily difficult. The signals are faint, obscured by the overwhelming light of the host star. However, techniques are being developed that rely on subtle gravitational effects. For example, if a moon is orbiting a gas giant, its gravity can slightly tug on the planet itself. By precisely measuring the wobble of the planet, astronomers can infer the presence of a moon, even if the moon itself remains invisible. The accuracy of these measurements demands incredibly sensitive telescopes and sophisticated data analysis. Several promising exomoon candidates have emerged. One of the most compelling is orbiting the giant planet HD 180-9733b, which itself is known to have a very eccentric orbit. Observations from the Hubble Space Telescope revealed a periodic dimming of the planet's light, a phenomenon that couldn't be explained by the planet's own variations. Subsequent research strongly suggested the existence of a moon, designated HD 180-9733bi, roughly the size of Earth's moon. While its existence hasn't been definitively confirmed, the evidence is exceptionally strong, making it a leading example of a potentially discovered exomoon. The size and characteristics of these exomoons are dramatically diverse. Some are likely to be small, rocky bodies, similar in composition to our own moon. Others could be significantly larger, possibly even gas giants themselves, though this is less commonly theorized. The conditions on these moons, temperature, atmosphere, and surface features, would depend heavily on their distance from their host star and the composition of their atmospheres. For instance, a moon orbiting a red dwarf star, which are smaller and cooler than our Sun, would experience dramatically different light conditions than a moon orbiting a Sun-like star. This has huge implications for the potential for liquid water and, consequently, the possibility of life. Furthermore, the dynamics of exomoon systems are thought to be far more complex than those within our own solar system. The gravitational interactions between a planet and its moons, and between multiple moons, can create chaotic orbital patterns. Some moons might have highly elongated, eccentric orbits, while others could be locked in tidal resonances with their host planets, perpetually displaying one face towards the planet. The study of these interactions is critical for understanding how these moon systems evolved and whether they could harbor stable conditions over billions of years, a crucial factor for the development of life. The discovery and characterization of exomoons isn't just about finding another celestial body. It's about broadening our understanding of planetary formation. Current theories suggest that moons often form alongside their planets, originating from a swirling disk of gas and dust that surrounds a young star. However, a different model proposes that some moons may form after the planet has already formed, through accretion, the gradual accumulation of smaller bodies. Finding exomoons can therefore provide valuable data to test and refine these theories. For example, if a large number of exomoons are found orbiting giant planets, it would bolster the accretion theory. Conversely, if only a few small moons are discovered, it might suggest a different formation process. The James Webb Space Telescope is proving to be a game changer in the search for exomoons. Its infrared capabilities allow it to detect the faint heat signatures emitted by these moons, even when they are obscured by the glare of their host star. Furthermore, Webb's precise spectrographic measurements can analyze the light reflected by a moon's surface, revealing information about its composition, the minerals and elements that make it up. This opens the possibility of identifying biosignatures, chemical indicators that might suggest the presence of life, although detecting life itself remains an immensely challenging task. The potential for liquid water is a central theme in the exomoon exploration. As we've discussed, the conditions a moon experiences are dictated by its distance from its star. Many scientists believe that liquid water is a fundamental requirement for life as we understand it. Therefore, finding moons within the habitable zone, the region around a star where temperatures are just right for liquid water to exist, is a high priority. It's important to note that habitable doesn't necessarily mean inhabited, but rather a zone where the necessary ingredients for life could exist. The search is thus a carefully considered one, focusing on environments with the potential for stable conditions and the necessary chemical components. Looking ahead, future missions are being planned to specifically target exomoon systems. These missions could employ a combination of techniques, including direct imaging, radial velocity measurements, and transit timing variations. The goal is to not only detect exomoons, but also to characterize their atmospheres, surface features, and orbital dynamics. The discovery of even a single definitively confirmed exomoon would represent a monumental achievement, fundamentally altering our perspective on our place in the universe. It would demonstrate that planetary systems and the possibility of life beyond Earth are far more common than we previously imagined. The exploration of exomoons is truly a frontier of scientific discovery, filled with both incredible challenges and the potential for profound revelations. The moon, as we see it today, a familiar companion in our night sky, isn't just a leftover chunk of rock. It's a remarkably ancient record, a silent observer that has borne witness to some of the most dramatic and formative events in the birth of our entire solar system. Its story isn't simply about its own creation, but about the chaotic, swirling processes that gave rise to everything we see around us, the planets, the asteroids, and even the sun itself. To truly understand the moon, we need to rewind the clock, back to a time when the solar system was a turbulent, almost unrecognizable place. Around 4.5 billion years ago, the region where Earth and the moon exist today wasn't empty. It was a protoplanetary disk, a vast swirling cloud of gas and dust, primarily composed of heavier elements forged in the hearts of dying stars. This disk, left over from a supernova explosion, was gradually accumulating material, drawn together by gravity. As it collapsed, it began to spin faster and faster, like a figure skater pulling in their arms. This rotation eventually led to the formation of a young sun at the center, surrounded by this burgeoning disk. The moon's origin is most widely accepted today as a giant impact event. A Mars-sized object, often referred to as Theia, smashed into the early Earth. This wasn't a gentle collision. It was a catastrophic, high-velocity impact that ejected colossal amounts of debris, material from both the Earth's mantle and Theia, into orbit. Over a relatively short period, perhaps just a few million years, this debris coalesced under gravity, gradually forming the moon. It's a truly astounding event, and the energy released would have been far greater than any explosion we've ever witnessed. What's particularly fascinating is that the early solar system was incredibly active. The bombardment wasn't just a single event. It was a sustained period of intense collisions. Other protoplanets, smaller than Mars, were also orbiting the sun, and they frequently crossed paths, leading to further impacts. These collisions weren't just about creating new bodies. They were also responsible for shaping the orbits of the planets, influencing their compositions and distributing volatile elements, things like water and methane, throughout the system. The moon, therefore, inherited a significant amount of material from this early, dynamic environment. The prevailing theory suggests that much of the moon's composition reflects the conditions present in the Earth's mantle at the time of the giant impact. This means that the moon is relatively depleted in siderophile elements, elements that preferentially react with iron compared to Earth. These siderophile elements, like nickel and cobalt, were essentially swept out of the Earth's interior during its formation. Looking at the Moon's geology provides crucial insights into this early solar system. Its crust is remarkably old, dating back to shortly after its formation. This contrasts sharply with Earth, where the crust has undergone numerous periods of upheaval and reformation. The Moon's surface is covered in a global layer of basalt, dark, fine-grained volcanic rock, formed by extensive volcanic activity that occurred billions of years ago. The relative lack of complex minerals and the presence of pristine, unweathered rocks on the lunar surface are a direct consequence of the Moon's youth and the lack of significant erosion processes. Scientists use lunar samples brought back by the Apollo missions, a treasure trove of information, to reconstruct this early solar system environment. Analyzing the isotopic ratios of elements within these samples reveals patterns that mirror those found in meteorites, which are believed to be remnants of the original protoplanetary disk. This provides compelling evidence that the Moon formed from material originating from this distant, swirling cloud. Furthermore, the Moon's orbital characteristics offer clues. Its orbit is slightly tilted relative to Earth's orbit, and it's also eccentric, meaning it's not a perfect circle. These characteristics are thought to be remnants of the impact event itself, and also reflect the gravitational interactions it experienced with the developing planets. Studying these orbital parameters helps scientists refine models of the giant impact and the subsequent evolution of the solar system. The Moon's existence played a vital role in stabilizing Earth's axial tilt. Without the Moon's gravitational influence, Earth's axis would wobble dramatically over long periods, leading to extreme and unpredictable climate changes. The Moon's presence has, over billions of years, provided a relative degree of stability, allowing for the development of a more predictable and habitable environment on our planet. Ultimately, the Moon isn't just a celestial body, it's a living time capsule. By studying its formation, its composition, and its characteristics, we're gaining a deeper understanding of the very origins of our solar system. It's a testament to the power of cataclysmic events and the intricate processes that ultimately gave rise to the complex and beautiful system we call home. The story of the Moon is inextricably linked to the story of our solar system, a silent witness to the universe's grand, unfolding drama. The Moon's surface isn't just dusty gray. It's a complex, layered material known as lunar regolith. It's a product of billions of years of bombardment, erosion, and subtle, ongoing processes, a record etched in stone and dust. Initially, the Moon's surface was smooth, formed by volcanic activity and impacts that melted and cooled the rock. But over immense timescales, this smoothness vanished, replaced by this distinctive layer. The precise composition of lunar regolith varies depending on location, with some areas showing significant differences in mineral content. The dominant component of the regolith is silicate material, specifically minerals like plagioclase feldspar and pyroxene. These are the building blocks of many rocks on Earth, but here they're found in a fragmented, weathered state. The intense heat of constant impacts from meteoroids and asteroids has broken down larger rocks into smaller particles. This isn't like how rain breaks down a cliff face. It's a far more violent process. Imagine repeatedly dropping a rock onto a hard surface. Eventually, it would shatter into fragments, and that's essentially what's happening to the Moon's surface. Another significant component is glass, often referred to as agglutinate. This glass isn't formed from molten lava, as you might expect. Instead, it's created when small, glassy beads form from the fusion of colliding particles. When two small rocks slam together at high speeds, the energy of the impact causes the particles to melt and mix, creating a glassy sphere. These spheres can grow by incorporating more surrounding material, becoming larger and larger over time. The distribution of these agglutinate grains is often seen in dark streaks and patches across the lunar surface. especially in areas that have experienced frequent impacts. The color of the regolith isn't uniform either. The gray color is due to the presence of iron-rich minerals, which were exposed to the surface by the constant impacts. However, darker patches, often referred to as black streaks, are made up of graphite, a form of carbon that was delivered to the moon by comets and asteroids. These dark streaks are particularly concentrated in permanently shadowed craters near the poles, where the carbon has accumulated over long periods, shielded from direct sunlight. The properties of lunar regolith are also unusual. It's incredibly fine-grained, with particle sizes ranging from dust to pebbles and even larger rocks. This fine-grained size makes it remarkably abrasive. A tiny amount of regolith can quickly damage tools and surfaces. This abrasive nature is why special equipment and techniques are required for lunar exploration. Furthermore, the regolith exhibits a unique electrostatic charging behavior. As particles rub against each other during movement, due to the lack of atmosphere and the constant bombardment of solar radiation, they accumulate static electricity. This causes the regolith to become charged, attracting and holding dust, creating a persistent haze that can obscure the view of the lunar surface. The processes that modify the lunar regolith are ongoing. Micrometeorite impacts continue to break down rocks and create new grains. Solar wind, a stream of charged particles emitted by the sun, interacts with the regolith, sputtering off atoms and ions, further altering its composition. This sputtering process is a slow but constant erosion mechanism, gradually removing material from the surface. The distribution of regolith across the moon's surface is also far from uniform. Impact craters, created by large asteroid and comet impacts, have excavated and exposed deeper layers of the regolith. These craters, ranging from small depressions to enormous basins like the South Pole-Aitken Basin, provide access to the moon's interior and showcase the different layers of the regolith. The depth of the regolith varies considerably across the lunar landscape, influenced by the history of cratering and erosion in each area. Furthermore, the lack of a substantial atmosphere on the moon means that wind, as we know it on Earth, doesn't exist. However, solar wind and micrometeorite impacts still generate forces that move the regolith. This movement, combined with the electrostatic charging, contributes to the formation of drifts and flows, shallow, moving sheets of dust and small particles that cover large areas of the lunar surface. These drifts are a visible manifestation of the ongoing processes shaping the moon. Scientists study the composition and properties of lunar regolith to understand the moon's history, its formation, and its evolution. By analyzing the different layers of regolith, they can reconstruct the sequence of impacts and other events that have shaped the lunar surface over billions of years. The regolith, in essence, is a time capsule, preserving a record of the early solar system and the violent processes that have occurred since its formation. Future lunar missions will undoubtedly continue to unlock more secrets hidden within this fascinating, complex material. The exploration of the moon's regolith is a vital step in understanding our own planet's past and paving the way for future human exploration. The moon, so silent and still, doesn't just sit there reflecting sunlight. It's constantly subjected to a powerful, invisible force, solar radiation. This isn't the gentle warmth of a summer afternoon. It's a barrage of energy from the sun, a truly intense environment unlike anything found on Earth. The sun doesn't just send light, it sends particles, and these particles are incredibly energetic. They're mostly made of hydrogen and helium ions, stripped away from the sun's atmosphere and carried outward by the solar wind. When these particles hit the lunar surface, they trigger a remarkable set of processes, fundamentally altering the very composition and appearance of the moon. The lunar surface, covered in a layer of material called regolith, a mixture of dust, broken rock, and tiny glass shards, provides a perfect laboratory for observing these effects. The regolith isn't a solid, uniform substance. It's incredibly porous, with lots of tiny spaces and grains of varying sizes. This structure is key to how solar radiation interacts with it. The grains themselves are composed primarily of silicate minerals, similar to those found in Earth's rocks, but their crystalline structure is significantly altered by the constant bombardment. One of the most noticeable consequences of this bombardment is a phenomenon called solar wind charging. The solar wind particles, carrying a negative electrical charge, repeatedly strike the regolith grains. Because the grains themselves often have a slight positive charge, these impacts cause a transfer of electrons. Essentially, the solar wind steals electrons from the lunar dust, leaving the grains with a net positive charge. This creates a static electric field across the lunar surface, a shimmering, invisible electric blanket powered by the sun. This charging isn't just a curious observation, it's a significant driver of other processes. The charged regolith can attract and hold onto other charged particles, both from the solar wind and from cosmic rays, which are high-energy particles that constantly stream through space. This accumulation of charged material forms what scientists call radiation traps, areas where the concentration of charged particles is significantly higher than the average. These traps are particularly abundant in permanently shadowed regions of the moon, like those found within the craters near the poles. But the effects of solar radiation extend far beyond simply charging the regolith. The high-energy particles within the solar wind aren't just interacting with the dust, they're actively altering the minerals themselves. This process is called micrometeoritic bombardment, and it's a key component of the weathering of the lunar surface. Imagine throwing tiny pebbles, much smaller than grains of sand, at a stone repeatedly over a very long period. The constant impacts cause the minerals in the regolith to fracture, break apart, and even vaporize. The solar wind's energy is sufficient to break down the chemical bonds holding together the crystalline structure of minerals like plagioclase feldspar, a common component of the lunar rocks. This process produces new, volatile compounds, including water ice and hydroxyl OH, which were surprisingly detected in permanently shadowed craters. The presence of these volatile compounds is a fascinating discovery, and it offers clues about the moon's history and its potential for future resource utilization. Furthermore, the thermal effects of solar radiation play a crucial role. The lunar surface heats up intensely during the day, absorbing vast amounts of solar energy. This heat causes the regolith to expand and contract, creating stresses within the material. When the surface cools rapidly at night, this expansion and contraction cycle repeats, further contributing to the breakdown and modification of the regolith. The combination of thermal stress and constant bombardment is incredibly powerful, slowly eroding the lunar surface. Scientists use sophisticated instruments, like spectrometers, to analyze the composition of the lunar regolith and to measure the effects of solar radiation. These instruments can detect changes in the abundance of different elements and minerals, providing a detailed record of the ongoing weathering processes. They've found evidence that the solar wind is not just eroding the surface, but also changing its color, transforming darker areas into lighter shades. This is due to the alteration of the surface minerals, exposing new, brighter materials. The rate of weathering on the moon is significantly faster than on Earth. This is because the moon lacks a substantial atmosphere to shield its surface from the solar wind, and because it doesn't have plate tectonics, the geological process that constantly renews and recycles the Earth's crust. The constant, unrelenting assault of solar radiation is gradually transforming the moon, carving out its landscape and reshaping its surface, a testament to the immense power of the sun. This ongoing process will continue to sculpt the lunar landscape for billions of years to come, and studying these changes helps us understand not only the moon's past, but also the broader processes that shape planetary surfaces throughout the solar system. The dream of a permanent human presence on the moon has steadily grown, fueled by technological advancements and a desire to expand our reach into the solar system. It's no longer simply a scientific curiosity. Increasingly, it's being viewed as a crucial stepping stone for further exploration to Mars and beyond. But establishing a sustained lunar settlement isn't just about landing a flag and planting a tree, though those have been considered. It's a profoundly complex undertaking demanding a deep understanding of the moon's resources and a significant amount of creative problem-solving. The fundamental question becomes, how do we make the moon habitable, and more importantly, how do we sustainably live on it? Initial plans, often termed forward bases, primarily focused on small, relatively self-sufficient research outposts. These would be vital for conducting scientific experiments, studying the lunar geology, analyzing the solar environment, and perhaps even observing Earth from a unique vantage point. However, the goal of a truly permanent settlement necessitates considering resource utilization, and this is where things become particularly fascinating and challenging. One of the most actively explored possibilities is utilizing the moon's regolith, that ubiquitous, finely grained dust covering the surface, as a building material. It's abundant, and surprisingly, it possesses certain properties that could be leveraged. Robotic construction systems are being developed to 3D print structures using the regolith, mixed with binding agents. This approach offers a significant advantage over transporting massive amounts of materials from Earth. Furthermore, the regolith contains valuable minerals, including ilmenite, a titanium iron oxide that could be processed to create oxygen, a critical component for breathable air and rocket propellant. Extraction techniques are being tested, utilizing methods like microwave heating to liberate the oxygen. The challenge, however, lies in the dust itself. Lunar regolith is incredibly abrasive, capable of damaging equipment, and posing a serious health hazard to humans if inhaled. Mitigation strategies, specialized suits, airlocks, and dust mitigation systems are paramount. Beyond construction and oxygen production, the moon's water ice, discovered in permanently shadowed craters near the poles, represents another game changer. This water isn't just a precious resource for drinking and sanitation. It's a source of hydrogen and oxygen that can be split through electrolysis to generate rocket propellant. Establishing a propellant depot on the moon would dramatically reduce the cost and logistical complexity of future missions to Mars and elsewhere. However, accessing this ice isn't a simple task. These shadowed craters are extremely cold, and the terrain is rugged and treacherous. Robotic missions are necessary to identify and extract the ice, and even then, the extraction process requires careful energy management. The concept of closed-loop life support systems is central to the feasibility of a lunar colony. Because transporting supplies from Earth is incredibly expensive, colonists would need to recycle nearly everything: water, air, and even waste. Advanced bioreactors, utilizing algae or other microorganisms, could be employed to convert carbon dioxide into oxygen and biomass, providing food and fuel. These systems would need to be incredibly reliable and robust, capable of operating autonomously for extended periods. Another element of this is food production, and while large-scale agriculture is unlikely given the challenging environment, research into hydroponics and aeroponics is showing promise. Creating a controlled, artificial environment for growing crops would supplement any manufactured food. Habitability presents a series of interconnected problems. The moon's surface experiences extreme temperature variations, ranging from scorching heat in direct sunlight to frigid temperatures in the shade. Maintaining a stable, comfortable environment inside a habitat would require sophisticated thermal regulation systems. Radiation shielding is also a major concern. The moon lacks a substantial atmosphere and magnetic field, leaving its surface exposed to harmful solar and cosmic radiation. Habitats would need to be built underground or shielded with layers of regolith or specialized materials. Furthermore, the lunar day, lasting approximately 14 Earth days, is significantly longer than the night. This long period of sunlight could lead to overheating if habitats aren't designed with careful consideration for solar gain. The psychological impact of living in a confined, isolated environment on the moon is another consideration. Long-duration missions have demonstrated that isolation can negatively affect mental health. Careful crew selection, robust communication systems, and opportunities for recreation would be crucial for maintaining morale and well-being. Designing habitats to foster a sense of community and connection would be just as important as their physical functionality. Looking further ahead, the possibility of lunar mining, extracting valuable resources like helium-3, a potential fuel source for fusion reactors, is being investigated. However, this would necessitate the development of sophisticated mining equipment and processing facilities, adding another layer of complexity to the endeavor. The goal isn't simply to extract resources. It's about establishing a sustainable economic base on the moon, one that could eventually support a thriving lunar settlement. Ultimately, creating a permanent human presence on the moon is a monumental undertaking, a convergence of engineering, science, and human resilience. It demands a thorough understanding of the moon's unique challenges and a willingness to adapt and innovate. It's not just about planting a flag. It's about building a future beyond Earth, one that begins with a foothold on our nearest celestial neighbor. The moon, silent and stark against the velvet black of space, isn't just a beautiful celestial neighbor. It's become an extraordinary laboratory, a place where we can test the very foundations of our understanding of the universe. Scientists are increasingly recognizing that the moon's unique characteristics, its low gravity, its exposed surface, and its isolation from Earth's atmosphere, offer unparalleled opportunities to study fundamental physics in ways that simply aren't possible here on our planet. The key here is a very careful look at gravity, how time behaves, and the properties of the vacuum itself. Let's begin with gravity. On Earth, gravity is a constant, a force that shapes everything from the flow of water to the trajectory of a thrown ball. However, the moon's gravity is considerably weaker, about 1/6 of Earth's. This difference is vitally important. It allows scientists to observe objects and even entire experiments in ways that would be impossible on Earth. For instance, a small, lightweight device, designed to withstand the harsh lunar environment, can be propelled across vast distances with relatively little force. Researchers have used this to study the behavior of dust particles in low gravity, observing how they move and interact in ways dramatically different from their behavior on Earth. This isn't just a quirky observation. It's revealing new insights into fluid dynamics and granular materials, things that influence everything from the formation of galaxies to the way powders flow in our own kitchens. Furthermore, the reduced gravity facilitates incredibly precise experiments involving inertia. Inertia, in simple terms, is the tendency of an object to resist changes in its state of motion. Newton's second law states that force equals mass times acceleration, F equals ma. While this law holds true on Earth, it's more easily demonstrable and measurable in the moon's lower gravity. A small object, like a bouncing ball, will exhibit a much larger acceleration, making its motion easier to track and analyze. This is particularly relevant when studying the behavior of complex systems, like those found in biological tissues or advanced robotics. Researchers are using lunar experiments to refine our understanding of how forces affect motion, leading to improvements in areas like spacecraft design and even athletic training. Now, let's consider time. The moon's lack of atmosphere and its distance from Earth create a remarkably stable environment, and this stability is profoundly affecting our ability to study the passage of time itself. On Earth, time is constantly affected by subtle vibrations and fluctuations, things caused by weather patterns, seismic activity, and even the electromagnetic radiation from the sun. These effects, though minuscule in most cases, can accumulate over time and introduce inaccuracies in extremely precise measurements. The lunar surface, shielded from these disturbances, offers a remarkably stable platform for conducting long-term experiments with atomic clocks. Atomic clocks, the most accurate timekeeping devices ever created, rely on the constant, predictable oscillations of atoms, specifically cesium atoms. The Moon's environment allows for uninterrupted observation of these oscillations, providing scientists with a baseline against which to test theories about time dilation, a concept famously explored by Einstein's theory of relativity. Essentially, relativity predicts that time passes differently for observers in different gravitational fields or who are moving at different speeds. Experiments on the Moon, where the gravitational field is weaker than on Earth, can help to confirm and refine these predictions. It's like having a perfectly still and quiet location to listen to the universe's heartbeat. The concept of the vacuum is also undergoing a fascinating transformation through lunar research. On Earth, the vacuum is constantly bombarded by molecules from the atmosphere, creating a complex and dynamic environment. However, on the Moon, the vacuum is pristine, a truly empty space. This allows scientists to study the behavior of materials in a vacuum with unparalleled clarity. For instance, they can investigate how materials change under extreme conditions, such as extreme temperatures or radiation exposure, without the interference of atmospheric gases. Researchers are studying how metals and semiconductors behave in a vacuum, which is crucial for developing new technologies like advanced sensors and high-performance electronics. They're also investigating the properties of the lunar regolith, the powdery surface material, in a vacuum, to understand how it reacts to radiation and temperature changes. This information is critical for designing habitats for future lunar explorers, where it's essential to protect sensitive equipment from the harsh space environment. The study of the vacuum on the Moon isn't just about space exploration. It's about understanding the fundamental nature of empty space itself, a place we often take for granted. Furthermore, the Moon's vacuum provides a valuable tool for creating extreme environments for materials science research. By precisely controlling temperature and pressure within a vacuum chamber, scientists can simulate conditions found deep within the Earth's crust, or even in other parts of the solar system. This allows them to study the behavior of materials under conditions that would be impossible to recreate on Earth. It's a miniature, controlled version of the universe's most extreme environments, all contained within a lunar habitat. The possibilities for discovery are, quite literally, out of this world. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The Moon's secrets now rest gently in your memory. Let your thoughts drift, calm and unhurried until sleep finds you.